Right. First of all, I must thank Professor Chan for giving me this opportunity to share with you the work that we've been doing over the years. I come from an engineering department, so the content of my talk is of a slightly different tone, in a different flavor. We focus more on the application side of Plasmonics. I hope I can generate some questions, particularly from the students. I have about 80 slides. I must warn you for this, but if time is limited, I mean, it depends on my speed. Since this is rather informal, I imagine, I might actually, jump to the conclusion and without finishing the last part, which is actually lab on the chip work, with lab on the disk work that we've been doing in the past couple of years, which I find very interesting. So let's see how we get on, because I understand we already overshoot our schedule. So the topic of my talk is optical biosensing. It's an interdisciplinary research topic between photonics, nanotechnology, and biological sciences. This is the outline of my presentation. I'll first talk about surface plasmon resonance sensors, and then plasmonics in nanoparticles, particularly nanocrystals of metal, and then followed by plasmonic optical trapping, and then about 15 or so slides on lab on disk, and then finally conclusion. This is the introduction, actually. I mean, it's all about plasmonics, and they give characteristic colors to noble metals. It's all because of the dielectric constant being complex, with a negative real part and then an imaginary part as well. And they all have different plasmonic resonance wavelengths, and therefore give you the characteristic color and make them so beautiful. Plasmonics is all about electromagnetic wave impinging a metal object and then sending the electrons to move around as a consequence, and it depends on the size and the population, i.e. density of the electrons in the object. They tend to resonate because it is round-trip consideration, and so it depends on the shape and size and the electron density as well as dielectric constant of the object. And for the electrical engineer, we deal with communication. So this is exactly the Yagi antenna that we are so familiar with, that the impinging radio wave sends the electron in the metal object to resonate and therefore give you a signal, except that they work in much lower frequency, in the range of 100 megahertz, whereas in the optical case, it's 100 of terahertz. Over the years, the chemistry people have developed recipes to generate very regular nanoparticles of metal, nanocrystals, and because of the resonance frequency, they tend to scatter very selectively with certain wavelengths. And you can see that these, maybe I'll use that one then. These nano rods of different aspect ratios tend to resonate at different colors and therefore give you very colorful images. And in fact, the resonance depends very much on the size as well as the surrounding environment of the nanoparticles. And also they are so good for scattering and very strong signal and localized field, as we all already know that plasmonics tend to enhance the field on the surface of the object. And therefore give you a channel for performing highly sensitive fluorescence-free real-time biosensing applications. So for the application, this is a schematic showing us how we can use it. Basically, we can functionalize the nano object with a molecule, for example, a protein, say an antibody. And then the antibody will selectively bind to its target antigen. And because it's within the vicinity of the nanoparticle, the localized enhanced field will actually interact with the target molecule, which has been captured, and then give you a strong signal. So in that process, we can have highly sensitive biosensing. We can also do trapping because of the localization. There is a strong gradient field surrounding the metal object. And over the years, people already sort of developed things like this, like in the conventional biosensing strategy, you have the antigen grabbing its antibody target, or vice versa, you can do the opposite. And then you label, you put a fluorophore, and then the presence of the target gives you fluorescence. But tend to photo bleach, and they also have limited choice of multiplexing, i.e. the wavelength of the emission tend to overlap. And they also may affect the biomolecular reaction, the actual reaction. Whereas plasmonic biosensing, it's known for its label-free real-time detection. And also, if you put a Raman tag as a probe, then the Raman fingerprint will give you multiplex signal. Except that, in fact, this looks good. However, the sensitivity that you can get out of this kind of detection is, compared to the fluorescence method, is still quite limited. Usually, you talk about 1,000 times less sensitive compared to fluorescence. But up until a few years ago, people already developed assays which involves plasmonics, in other words, nanoparticles of metal, and give you comparable sensitivity. We are now sort of approaching the attomolar level. Fluorescence is 20, whereas the plasmonic detection is 30. Okay, we are basically using this figure as if finding needles in a haystack. In the next slide, we'll probably see what we really mean. The typical concentration levels that we are talking about in real samples is, for example, circulating tumor cells, which is a good monitor for cancer patients. You're talking about, every 10 cells per mil, that is 1 in 10 to 9 cells. Or cancer biomarkers, in other words, proteins, in picogram per mil. In fact, it's actually 1 in 10 to 12 by weight. So, and then if it's oligonucleotide, i.e. DNA related molecules, we are talking about several copies per sample. So in the picture below, you can see that we are really trying to fish out very low concentration molecules and then give a signal. However, as time goes on, things like this actually keep coming up in the market. This is the latest. I mean, a few months ago, published report that a standard prostate cancer detection, typically they use ELISA, which is a very well-established technique to do such tests. Basically, you have a test strip, and then the test strip is sensitized, functionalized with a certain antibody, and then it tries to detect its target antigen. In this case, it's actually PSA, prostate-specific antigen. And you can buy kits like this, and it's 3 picogram per mil detection limit. It costs you $270 US. And now, for $10, you use nanoparticles of magnetic ferromagnetic oxides. And then they basically attached to to a binder. In fact, the target molecule is the center one. The presence of the target molecule will actually bind both the surface as well as the mass loading, if you like, magnetic beads. So now you've got, a lump of material being detected, and then you can actually detect that using conventional weight sensitive or magnetic or photonic techniques. And the detection limit is about 10 times better. So this labeling technique is very useful. Now let's go back to surface plasmons. Now we know that, in fact, if we have nanostructures, like for example bow tie and then a sphere on the bow tie or a sphere alone, then the sphere on the bow tie case, because of the gap, that gap gives you very strong field enhancement, and you can see the field enhancement ranges from 5,000 in the bow tie case, and then the isolated sphere around 800 to 500,000, simply because of the field localization. So in plasmonics sensing, it's all about enhancing the field where the molecule sits. Or you can actually do very simple thin film. Okay, you can actually generate plasmons in a thin film or periodic rulings, gratings. As far as our work is concerned, over the years we've been working with thin film, so a conventional inverted prism case. Very simple, very low cost, very easy to deal with, and you're guaranteed to get results. So it's good for a researcher like us. Don't need to spend too much money and you get good results. Basically what you do is you have a thin film of gold coated on a glass prism, and then you illuminate the prism from the opposite side, and then total internal reflection will send the optical beam parallel to the gold surface, and then that parallel beam will excite movement of electron, so that it then later becomes a surface plasmon polariton. So it's basically a coupling prism scheme that guides the surface plasmon polariton on the surface, and therefore you get enhanced field on the surface only, and then it interacts with the target molecule and then give you signal. Now that is a resonance effect. In other words, it only happens to a certain set of conditions, relates to the thickness of the film and the dielectric constant of the solution on the other side, i.e. where the molecules are, as well as the wavelength and the angle and so on. So these are the conditions for the matching phenomenon. So the conventional SPR sensor which you can buy is you illuminate the film with a range of angles, i.e. a beam, focusing beam from a cylindrical lens, and then the exit beam will then have a range of angles, and you detect it with an array of detectors. And then where surface plasmon resonance happens, then the beam gets absorbed by the plasmon, and therefore you get a dip if you plot angle versus reflection. And the dip is related to what's going on the surface. So if you have molecules now being immobilized to the surface, then the refractive index on the surface changes, and therefore it shifts the dip, and then you get detection. Well, it's been used so widely. So what is our contribution? I thought, well, resonance also goes along with phase change. So if you do Fresnel analysis of the system, on top of the absorption dip, the phase of the incident beam also undergoes very sharp change. So sharp that it's almost vertical. In other words, if you actually detect the molecules near that region, you get very high sensitivity, because any tiny change of the refractive index on the surface will send the phase to a very large step change. if you look at the possible sensitivity limit, you talk about 10 to the minus 8 refractive index unit resolution. So this is our experiment. So basically a prism, gold film, and then molecules on the surface, and then it tries to detect its target molecules. And since we are detecting the phase, we use a Mach-Zehnder interferometer, and this is where our contribution comes. In fact, what we found was when you detect phase, if you detect a differential phase, i.e. phase that has been affected by the surface Plasmon effect, as well as the phase that has not been affected by the surface Plasmon resonance effect, we do the comparison between the two so that anything that doesn't come from the resonance should be eliminated. And this is exactly what happened. Basically, we are having two interferometers working in parallel. One is P polarization, which is affected by surface Plasmon. The S polarization doesn't. So we get enhanced sensitivity through the differential phase measurement. Indeed, this was done quite a few years ago, and we tried it. Once we tried it, it was so good, we never wanted to go back. We always stick with phase measurement, and you see later that over the years we've actually further developed this setup and make it even more commercializable. So this is their setup in the lab, and this is the result, which really confirms that we are getting 10 to the minus 8 refractive index unit regime with water, glycerin mixtures of different concentration levels. And then we also did some detection of DNA. We have a probe DNA, and then we tried to detect the human herpes virus DNA. And also we had a labeling DNA. In fact, that actually also gives us enhanced signal because of the loading effect. Okay, so the presence of the target DNA will actually bind to both of them, and to give us signal enhancement. In the end, we actually could detect DNA, but that's label-free and it's real-time. So then the system started to evolve, and we move on to, instead of using a laser beam, we use white light. Okay, white light of different frequencies give you different momentum, and they also have different resonance. So this is actually white light alone from the LED, and different refractive index give you different refraction depth in the spectral range. Okay, that's not very sensitive because the white light spectral detection, it's very difficult to locate the depth very precisely. So the resolution, you may be looking at about 10 to the minus 6 refractive index units. We combine that white light technique with the interferometer technique as if it's like an OCT, optical coherence tomography system, which is like this. Okay, so interferometer, white light, with very little coherence, so we had to put a dispersion compensation reference prism to make sure that the two beams interfere correctly. And then we detect S and P phase output, and then we can do the comparison. And that's very interesting because if you that's the actual setup. Okay, so light coming from the fiber, and then the two prisms, and then one of them is actually holding the sample, and then the exit beam goes to an interspectrometer. Now, because we are putting white light in the interferometer, it basically undergoes wavelength selective interference. So the blue line, the blue plot is P polarization, which is SPR sensitive. The red line is S polarization, which is not SPR sensitive. Okay, and then therefore you don't see any absorption. And the fringes is because of the path difference as you change the wavelength in the interferometer. Now that's water, and that's 10% NaCl, and you can see the dip actually shift. Okay. Now within those, you can actually see some structure. Let me just use the structure is that before resonance, they're all in phase, or almost in phase. Okay. Whereas after resonance, you have immediately shift to outer phase. It's all because of the resonance effect. The system goes in phase and out of phase. And because of that, if you actually do Fourier transform, the entire structure will give you phase measurement. So it gives you very high sensitivity, and yet it also gives you very wide coverage of the refractive index. Okay, so we did some bio-testing, and then it did work with some protein, BSA, anti-BSA detection, and the sensitivity limit is about 0.5 nanogram per mil. Now this is the last version of, the latest version of our machine, which we actually wanted to do a startup with. And what happens is that in all our previous design, we had interferometers. We had 2 arms that need to be interfering very, very accurately, otherwise you lose signal. And it's a pain, actually, particularly if you want to change angle. So it's not that practical for real use. So then we decided, this is actual machine that we made in the end. This is setup. So we actually interfere the white beam, white color beam, before it goes into prism. Okay, before it goes into prism, and then it suffers SPR change phase, and then there is another beam which actually goes through a reference. Okay, so we measure the reference before SPR action, and then we measure the signal after SPR, and then we compare the two, which actually exactly the same as what we saw before, except that we're not detecting them from the same beam, but it seems to work very well. And now we have removed the requirement of having to put the prism within the interferometer. So we have taken away the alignment requirement, if you like, and it makes it a lot more practical. And so hopefully we can really make real machines out of this. And this is actually a prototype that we try to show to people and attract some investment funding. Over time, we have done other tricks. For example, we put nanoparticles of gold on the surface, and then energy coupled from the surface to the nanoparticle. If you do FDTD measurement, you actually see very high field in the gap, and then that high field gives you very significant phase jump. We used the same interferometer to do the phase jump, and then we actually found out that if you optimize the diameter, you get good sensitivity, about 100 times enhancement in the D field. We also did other experiments. For example, try to restrict the number of molecules that you can get out of a gold nanoparticle. Now, in this game, you are functionalizing the surface of the nanoparticle with target molecules. Now, typically, if you have a sphere, you may be looking at, in this case, 5 molecules on the surface simultaneously. Okay? And then each one of them can give you binding. So you can't quantify, you don't know how many. Could be somewhere between 0 to 5. Okay? Now, the chemistry department has our collaborator designed the crown ether monolayer. That crown ether monolayer has a loop, and the loop can actually restrict the functionalization so that each nanoparticle, in this case, receives only 1 molecule for the functionalization. So you then get direct quantification because each nanoparticle is equivalent to 1 molecule. And you get very large signal amplification because of the fact that you now have very high series loading from the gold. So that sort of wraps up our surface plasmon resonance sensor. And then we did some work on surface-enhanced Raman scattering. What we did was to try and look at the best substrate we can get. So we did systematic analysis of gold and deposit nano-islands of silver on gold, and then change the deposition conditions and look at the resonance. So we did a set of experiments with the gold, the silver thickness ranging from nominally 10 angstrom to 90 angstrom, 5 samples we made. And then we look at the Raman signal from a Raman tag, and we found that the 50 angstrom one was the best out of those 5. And then we analyzed what happened. What we saw was very interesting. The absorption of that film happens at the maximum 552 green, okay, nanometer. And then the excitation laser we use, it's actually an argon green laser 4514. And then the Raman scattered wavelength comes out at 562. And you can see now we've got 3 arrows. The peak is at the center. Excitation is on the shorter side. Emission is on the longer side. And then we actually came to conclusion, in fact, this is actually best. The enhancement factor is higher because the crystal absorbs strongly from the green laser, but emits radiation that doesn't absorb that strongly. And therefore, we get good enhancement factor because we suffer less loss. So we finished that and reported it. Then now we move on to metal nanocrystals, and this is actually a summary of what people can make these days, all kinds of shapes and sizes. And then you can functionalize them, and then through that you can do biodetection. You have just rod or particles or even core shell. Okay. And we focus on a specific type called silver nanodecahedron. Silver has better performance than gold, but gold has, because it's less loss, gold is very lossy. But people use gold all the time because gold actually covers a very wide range of wavelength, particularly from red to green region, which is very good for bio because bio doesn't like blue. There's a lot of fluorescence. Okay, gold is suitable for bio because it actually has plasmon resonance near green and red. Silver doesn't. So we then thought, well, if we can make silver that resonates in the green-red region, then it's a good idea. So we then decided, well, in fact, you do have this kind of outcome using silver nanodecahedron. So we use a solution-based growth technique and then generate these double-sided 5-facet crystals of silver. We can control the size, and then they resonate at different wavelengths. In this case, it's actually up to 590, which is sort of orangey red. And you can see that they're very monodispersed characteristics. In fact, the latest we found is actually 620. We can make them bigger so that they become 620 in resonance. Okay, and later we actually put coating on them and then embed the coating, silica coating, with Raman tags, and then they become Raman active as probes, so that you can use them as Raman labels for molecules. And then using the same solution-based growth technique, which actually initiated through illumination, light. We actually use a prism coupler to generate gratings on a glass surface. And then the grating glass surface, in fact, leads to growth of quasi-gratings. And the quasi-gratings, in fact, contains a lot of silver nanoparticles on the glass substrate. And you can see that they actually have they can change the periodicity, and then you can actually get very, very shiny scattering with good uniformity. And those gratings, we pass them to our collaborators in Hong Kong U, who make organic OPVs, organic PV devices, and they actually make good use of it. The first one is the grating. If you actually put them under the solar cell structure, the electron hole pair are now generated near the grating. Instead of the conventional situation, the electron hole pair is generated near the surface. Okay. If the electron hole pair is generated near the surface, then the holes have to travel a long distance to the collector electrodes. Whereas if it's on the grating, then it has to travel a very short distance only. And that makes it very different because holes tend to have lower mobility. And therefore, in this case, the incorporation of the grating will actually improve performance because of the breaking space charge limit. We also did some analysis on the physics of the gratings, which actually have a long-range order as well as short-range disorder. And they seem to have a different diffraction mode than the perfect case, i.e. simply grating only or random particles only. The next part is on nanoparticles in arrays. We haven't done a lot of experimental work on this. We did a lot of modeling work. The first one is nano waveguides, so that the confinement is within the nanoscale. So here you launch light into an array of nanoparticles, and then hopefully it guides the light and then emits from the other side. Plasmonics is known to be lossy. So if you launch light into an array of plasmonic nanoparticles, after some distance it just disappears because of absorption. So we actually did some modeling on what happens if you embed the particles in a gain medium. In other words, dope it with dye and then you pump the thin film and make sure that it's full of photons everywhere, and then hopefully light doesn't die away and hopefully we get gain out of it. So we actually did some optimization. It did actually find that right dielectric constant, i.e. right doping level of certain polymer could actually give us loss compensated waveguide. And then we expanded that technique into two-dimensional arrays of nanodots of gold, and then we also do pumping, and then again we can actually do amplification even of light plasmonic radiation being guided with gain. Another one is what we call dressing the resonant ring. That is basically like a guitar, and then you use a guitar to enhance resonance. Okay, so the guitar is dressing the resonance of your strings. So in here, what we've done is actually we use a ring, a dielectric ring, and try to enhance the resonance of a nanoparticle sitting in the center where the split is. Okay, there's a gold nanoparticle here, silver. Okay, and then that silver nanoparticle, if you put a tiny bit of target molecule, say another silver nanoparticle, that silver nanoparticle object will actually change the resonance intensity a lot. Okay. So in other words, we can actually measure the far field scattering intensity with anything very tiny bit of loading to the surface of the nanoparticle because of the ring. The ring tends to enhance the resonance. It doesn't work. It does now. Okay, so next part is on nano trapping. This is a slide that summarizes some of the reported work. People actually have been working on antennas, nano antennas, i.e. a bow tie gap or just a tiny gap. Then when you shine light to this bow tie gap, it tends to confine the field. Then the gradient force will actually give you trapping, and it actually beats Brownian motion. Okay, typical trap is like this, and it's actually a very large scale, whereas a plasmonic gap gives you a trapping appearance in nanoscale. People have done a lot of such work. They all require nanofabrication. Oops. So we did some modeling, designing, for example, plasmonic fluidic, so silver layers along the channel. And then the silver layer, if you actually create a gap, then if you shine light to this microfluidic channel inside which you have strips of silver, but creating a gap separated by some silicon quartz, PMMA layer, then we can actually create trapping simply along the channel. So the idea is, if you shine light to this channel, it traps your target. If you remove the light, then you release it, okay, and then let it flow. And then we also did some work on ring. So we modeled this ring, and we found that this ring resonates with certain radiation. This case, actually 785 nanometer. And then the ring gives you multiple trapping sites. But multiple trapping sites can be good because it gives you very large trapping area volume. Okay? The trapping volume is actually 10 to the 4 times larger than bow tie case. Okay? And in fact, the ring also gives you very good localization. Okay? So we have done some optimization and say that this actually has a very large trapping volume object. The final one is a conveyor belt. So we use 3 different sizes of disk. Because of their size, they resonate at green, red, green, and blue. And then they are polarization dependent. So as you can see in the next slide, if you actually use a certain polarization, the hot spots will be the top and bottom. And then you can see that as you switch wavelength, the different disk gets resonated. In fact, you can actually work out the forces of a particle, for example, polystyrene beads. You can actually move it along the edge of the disk. So if you actually do some simulation on how we actually move the thing, then in this animation, basically you can see that we can rotate the polarization, and then after we have moved to that side, we switch on the green, switch off the red, rotate the polarization, bring in the blue, switch off the green, then you can do conveyor belt. We did some optimization on the separation between the rings, bits, so that we can make sure that the operation of moving from one to the other, it's guaranteed. On the optical trapping, we thought of using a layer of random plasmonic structure, excite it, trap the target, and then use another laser to do some operation, and then release it. Now, people have done a lot of nano-fabricated structures, so we couldn't actually find much room to make contribution. We thought, well, people actually haven't looked at random nanostructures. So we actually decided to use random nanostructures, which is actually very easy to make. So you deposit the film on glass, in this case gold film, you then anneal it. Depending on the temperature and time, you actually form different nano-islands of different size and separation. So they resonate at different color, and therefore at different wavelengths, and therefore different colors. And then you shine light to this nanostructure from the other side, and you see that the localized field, which is on the surface, the gradient field will actually trap beads in water. Very efficient. You're talking about 10 to the 3 to 10 to the 4 times better than conventional optical tweezers. Very low power requirement. And this is a video which we captured. Something wrong with the resolution. So we shine light to it, and oops. So we're looking from the top under a microscope, and then as soon as we switch on the laser beam from the other side, then these polystyrene beads start to aggregate, and then as we switch off the laser beam, then they disappear. Very efficient. And then we move it to somewhere else. At the top is bare glass, okay? And this is actually gold-coated surface with nano-islands on. And then if we move the beam around, they follow. And then where there's no gold, disappeared. And then so we move it across, it's trap formed again. So very useful. We're still trying to work out the detailed physics of this thing. We tried trapping E. coli, so we also had some success. These are E. coli cells. And then we also did more work on putting the gold film on the fiber tip. So this is single mode fiber tip. So you can see the nano islands. So we look at the side view. So these are fluorescent polystyrene beads. So switch on the laser, particles start to aggregate more and more until it saturates. And then if you switch off the laser, it disappears. Okay. If you look at the top view, it's the same thing, except that you only see a few particles in this case. It's a different sample. So you can see nothing, switch on the power, and then start to aggregate, and then you form a lattice of nano polystyrene beads on the surface, and then take away the laser, switch off the laser, disappear. So we are still working on this, ongoing, and hopefully we can generate some good work. Very useful for trapping target. Now this is the final slide on Plasmonics, and this is what we plan to do. We've done a lot of inverted prism work. We've done a lot of biosensing. We haven't done femtosecond excited phenomenon. So I think we are going to incorporate femtosecond excited phenomenon coupled with SPP on the surface. We actually haven't done anything about ultrasound. In fact, in this system, if you look at non-destructive testing of material, they use the same setup, except that the source is an ultrasound probe. When an ultrasound probe arranged in this direction and it hits a boundary, it also generates surface acoustic wave, except that it's a mechanical wave, identical to SPP. And we want to see if we can actually do some coupling between ultrasound and plasmonic effects. And hopefully we can do some very high precision phase-sensitive detection, because we can now then shift the measurement modality to the mechanical wave phase quantity. So I think next step, we plan to do this with our CRF, and then we can do some interaction between sound wave and SPP. So lab on the disk, I think in the interest of time, it's not going to be possible for me to cover them all. A very quick word about lab on the disk is that 2 minutes. I hope that Professor Chan will allow me. Is that we make, lab on disk is basically, you put everything on a transparent microchannel environment, okay? So all the fluid flow, everything in there. With disk, you fabricate all the chambers in a disk. You spin. As you spin, the thing will actually move outwards because of centrifugal force, okay? You can control the spinning and then they control the centrifugal force very, very accurately. And it actually happens everywhere on the disk. So you have no problem with driving force because it happens everywhere on the disk simply by spinning. So very low cost. Okay? And then this actually is a video telling you that you can actually control the speed and controlling what happens to those fluid in the chambers. And then you can sequentially, okay, allow them flow into your reaction chamber. So in other words, you have achieved fluidic control with the use of spinning. Okay? And these chambers, say reaction agent B, reagent A, B, C, D, and then you can sequentially mix them. And then our contribution, what is it? Our contribution is electronics. Our contribution is electronics. What we found was all the reported cases of lab on the disk were passive. Okay? They didn't have the printed circuit board on the other side. They didn't have electricity. So we bring in electricity. So after we brought in electricity, things will be very different because then we can have local heating, we can have local control actuation, we can have local laser excitation and detection, and even data transmission, wireless module and so on. So we then did a lot of experiments and then demonstrated that it works, and then did a few experiments on allergy screening, DNA amplification, and blah, blah, blah. Very happy. And then I'm a happy man. So that brings me to the conclusion slide. So I've told you things about surface plasma resonance and plasmonics in nanoparticles, plasmonic optical trapping, and a little bit on lab on the disk. Thank you.
So now open for questions. How reproducible are these gigantic field enhancement 10 to the power something that you have these metal bars and then you put another metal particle on top of it, and therefore you squeeze the field to a very small volume and you get a gigantic enhancement. How reproducible are those?
They are not reproducible at all, actually. I mean, what people have done is they more or less do a very large scale, many such features on the surface and look for hotspots. So they just look for hotspots and then try to see, well, this is a very bright location and therefore high field enhancement. So it's random. No, you can't control it. Very difficult. Yeah. And that's the reason why we thought random structure might have some room to play, because by nature that is random, then we might be able to actually find a randomly locatable location. Yeah. And it's cheap. Very, very cheap.
Any questions? So I have one. So using structure, we measure phase change. I have a question. From opticals, there are many things will cause a phase. How do we know what you are detecting? I saw it detect different things, gave you different phase. But in the reality, what do you know what you are detecting?
Yeah, that's true. The selectivity comes from the biorecognition reaction. We cannot select in a sense. We're only detecting refractive index change.
Yeah.
So that refractive index change is, sort of assumed to be caused by a specific reaction, which is dictated by the molecules we have chosen. Yeah. We are not doing anything different.
Any other questions?
Any other questions?
Okay, if we don't have, so let's speak again.
Thank you. Thank you.